Imagine a metal that can remember its shape and return to its original form, almost like magic. But what if I told you this futuristic material is already on a mission to Mars? Today, we are diving into the fascinating world of nitinol, the shape memory alloy that is revolutionizing space exploration. When NASA first began planning for the Mars rovers, one of the biggest challenges was figuring out how to handle the harsh Martian terrain, which is rugged and unpredictable. The rovers needed tires that were incredibly durable and could withstand rough surface conditions without breaking. Traditional rubber tires were not up to the task. They could wear out quickly or even get punctured by sharp rocks and debris. And considering the extremely low temperatures on Mars, standard materials would become too brittle and would not survive long. That is where nitinol tires come into play. These tires are designed using nitinol's remarkable superelasticity, which makes them incredibly strong and able to deform under pressure, but also return to their original shape after the stress is removed. This ability to handle constant deformation without failure made nitinol an ideal material for the tires of the Mars rovers. Nitinol is a nickel-titanium alloy with two superpowers: shape memory effect and superelasticity. It was discovered in the 1960s at the U.S. Naval Ordnance Laboratory. Its name is derived from its composition, nickel and titanium, and the place of discovery. Let us first discuss the shape memory effect. When nitinol is deformed, it can return to its original shape when heated. This happens because of its unique phase transformation. To understand this, we need to talk about phase transformations in solids. In solids, phase transformations occur when a material changes its crystal structure due to changes in temperature or pressure. These transformations typically involve two different crystalline phases, and they can significantly impact the material's properties. In the case of nitinol, it undergoes a transformation between two phases: the martensite phase and the austenite phase. The martensite phase is a low-temperature phase. In this phase, the nitinol has a more flexible, deformed structure, which is why it can be easily shaped. When the temperature is lowered, the atomic arrangement changes, making the alloy more malleable. The martensite phase has a twin structure. The austenite phase is a high-temperature phase. When the nitinol is heated, the atomic arrangement shifts to a more rigid, ordered structure. So how does this magic metal property actually work? When nitinol is at room temperature, it is in its martensitic phase, and under normal conditions, it has a twinned structure, which is soft and easily deformable. Let us say we deform this twinned martensite. When we deform it, the bonds of the twinned martensite are not broken. Instead, they change their direction, causing the bulk material to deform without breaking. This deformed structure is called deformed martensite. Now, when we heat this deformed martensite, the bond arrangement changes again and converts to an ordered structure, which is austenite. As a result of this ordered structure, the material returns to its original shape. And when this heated material cools back to room temperature, it returns to twinned martensite. This is how the cycle of material structure returns to its starting point. And this property is called the shape memory effect. But what happens if we operate nitinol at a higher temperature? Specifically, if the operating temperature of nitinol is above the austenitic start temperature. Here, another property of nitinol comes into play: superelasticity. In fact, nitinol is mostly used because of this property. NASA has also utilized nitinol because of this feature. Superelasticity is like a superpower that lets nitinol stretch or bend significantly, but when the pressure is removed, it goes back to its original shape without heating, because the material is already at the austenitic temperature. Let us dive deeper into the concept of superelasticity. For superelasticity, nitinol is present at a temperature and pressure where the austenitic phase is stable. This austenitic phase has an ordered structure. When we apply a stress and deform nitinol, the ordered austenitic structure is converted to a stress-induced martensite phase. This martensitic phase is not stable at this temperature and pressure, so when the load is removed, the martensite is converted back to the austenitic phase. And this is how the material behaves as superelastic. Nitinol is not just used in space. It is a true game changer in many other industries, especially in medicine. Take stents, for example. These tiny devices, often made from nitinol, expand inside arteries to help keep blood vessels open. When inserted, they remain flexible, but once in place and heated, they expand to their preset shape, making them ideal for minimally invasive surgeries. In the world of fashion, nitinol is used in eyeglass frames. Thanks to its superelasticity, these frames can bend, twist, and return to their original shape, making them nearly indestructible. And in robotics, nitinol's shape memory effect is being used to create soft actuators, robots that can move and adapt more naturally than traditional rigid robots. These materials could open up new possibilities for surgical robots, prosthetics, and even space exploration. From stents in our bodies to tires on Mars, nitinol is everywhere, quietly shaping the future. But here's a question for you. If you could use shape memory metals for anything, what would it be? A self-folding car? A spaceship that repairs itself? Let your imagination run wild in the comments. If you enjoyed this deep dive into the science of nitinol, do not forget to hit that like button, share it with your friends, and subscribe for more fascinating content.